Okay. So now the first step will be to, let's say, write the equation, write the energy balance for the system. Our system is a cylindrical rod. So as usual, we start by writing the general equation, which is E dot N minus E dot out plus E dot generation equals to E dot stored, which is dE by dt for the system. Okay. But here, because we have, as usual, whenever you have constant temperatures, so here you have the surface of the temperature, the surface of the rod is at constant temperature. Okay. Because they said here, we don't want to exceed a temperature of 65 degrees on the surface. So we are trying to maintain a temperature of 65 degrees on the surface. That's why dE by dt is 0, since we are working with steady conditions. Okay. Now we have to compute what is E dot N, what is E dot out, and what is E dot generation. So as we said, we should know what are the different processes involved. So we go back to the given, we do a small figure. We have thermal resistance inside of our long cylinder. This will cause a generation heat. Okay. And to get the expression of E dot generation, we need to use the given. They told us in the given that the electric resistance per unit length is given by rho E over AC, where rho E is defined in the problem. The rho E is the electrical resistivity, okay? And AC is the cross-sectional area of our cylinder, okay? So to compute R prime electric, what is R prime electric? R prime electric is the resistance per unit length. And it's the electrical resistance, okay, R prime, it's electrical resistance RE over the length. So as usual, whenever we put a prime, it's per unit length. Okay. So here we already know from electricity that the power of generation in an electrical circuit is resistance times current square. Okay. And because we are doing the analysis per unit length, so we need the generated power per unit length. So we'll provide all values over L. Okay. And R over L is R prime. In this problem, they gave us R prime. They told us that R prime is the resistivity over the cross-sectional area of the cylinder. The cross-sectional area of the cylinder is pi d square over 4. This is the cross-sectional area of the cylinder. So we have AC is known, pi d square over 4. Okay. And we can calculate rho E, the electrical resistivity, from this formula. So all we have to do is the following. We just apply it, okay? Rho E 0 is given, we replace it. T, the temperature here, okay, is, they told us that this temperature represents the temperature of the bar material, okay? And since the temperature of the bar material is, we should not exceed this temperature of 65 degrees. So we are working under these conditions. We replace T by 65. T0 is given is 25. So we replace T0 by 25. Alpha is given. We replace it here. Rho E0 is given. The only unknown then will be rho E. We get the value of rho E. Once we get rho E, we divide it by pi d square over 4 of the cylinder. We get R prime E. And now we are ready to compute the expression of the generation flux, which is R prime E times I squared. In this problem, I is unknown and we want to calculate it. Yani the only unknown in this problem is the current I. So we'll write the energy balance on, and from the energy balance, we'll be able to calculate I. Let us now compute the other terms. We already discussed that we have heat loss from the cylinder towards the surrounding by two modes of heat transfer, by convection and by radiation. And we don't have any source, inlet source. Okay, so we have, because of just we have generation inside, and we are releasing this heat to the surroundings through convection and radiation. So the balance will be that the generated power is equal to the radiation power plus the convective power. So as you can see here, we can put minus Q prime radiation because it's lost by the system, minus Q prime convection, plus I square R prime E equals to 0. Now, since this is computed per unit length, also we should give the radiation and convection per unit length. So as we discussed before, both convection and radiation are taking place through the lateral area of the cylinder. Okay, so this is the lateral area. Yani we turn 360 degrees. That's why to calculate it, it's pi d times L. So when we compute the transfer per unit length, when you do the lateral area over L, you will get just pi times d. That's why in the expression of the net radiation per unit length, we do minus, because it's lost to the surrounding, epsilon times pi d, which is the area per unit length, times sigma times t to the power 4. T here is 65. But please, we don't put 65 to the power 4. Pay attention. This is a very common error. We get wrong results. We should always in the radiation calculation put T in Kelvin, because T in degrees to the power 4, and if you do 65 to the power 4 minus 30 to the power 4, it's not like 65 plus 2, 73.15 to the power 4 minus 25 plus 273 to the power 4, because it's non-linear. It's not like delta T. Okay. It's okay. You don't have to do 273.15. It's fine if you do just plus 273 to the power 4 minus T surrounding, which is T infinity. This is the temperature of air. Sorry, here we say we use the surface temperature. Here it is the same. In particular, in this problem, it is the same, but pay attention. The radiation term, you will use the temperature of the conduit surface. Okay, so we'll call it here, they called it T surrounding. And in the computation of convection, you use T infinity of air. Okay, but here, because they have the same value, we don't have any confusion. But in case, let's say the surface temperature was, for example, 28, then you will use 28 here in the radiation term. So minus 30 plus 273 to the power 4. And of course, you multiply the result by epsilon pi d sigma. You get then the value of radiation flux minus how to compute H, the convective coefficient computed from the following empirical relation. And you have all parameters. They gave you C. How to know units? Please pay attention. Here you have what meter Kelvin, what meter minus 1.75 for CK minus 1.25. What do you mean by, do they mean by this? The units used are watt, meter, and Kelvin. So these should be in meter. Okay, so you cannot keep it in millimeter and just replace it. Pay attention to convert it to meter, because the constant units are watt, meter, and Kelvin. So these should be in meter. And delta T should be, for delta T, Kelvin or degrees, it doesn't matter because it's just delta T. It's linear. You don't have T to the power square or 4 or 3. And since it's delta T, it doesn't matter if you put in degrees or in Kelvin. It will give you the same result. So here, when you do T minus T infinity, you should put the temperature of your rod, which is 65. So here it's 65 minus T infinity of air, which is 30. and then you compute the value of your convective coefficient. Then you multiply by pi d times t minus t infinity. Also, it's 35. 65 minus 30 plus I square over AC equals to 0. As you can see, all parameters in this equation are known except the current value. So you can solve for the current value. And after this, after calculating the current, they asked you to compare the relative importance of heat transfer by free convection and radiation exchange. Whenever they ask you such a question, you can find the percentage of heat by convection compared to the percentage of heat by radiation. All you have to do is to say the percentage of heat that is released from the system by convection is equal to Q prime convection. So you do the ratio Q prime convection over the total heat that is released out. The total heat released out is the summation of Q prime convection plus Q prime radiation. And you already found each term separately, and you can just plug in here to find the percentage of convection relative to the total heat transferred out. And of course, you multiply by 100 if you want to get it in percentage. You multiply by 100%. If we look at numbers here, we can see that we have 55% of the, here just it's a typing error. Okay, it's 55%. You got 0.55, it's equal to 55%. So you have 55% of heat is released by convection and 45% by radiation. So both are important parameters. Okay, we cannot consider that any of the two is negligible compared to the other. Any question on this?
Oh, thank you, Professor.
Welcome. Okay, guys, so now I will assign for you videos to watch for next time. And we can continue to do some problems and introduce the concept of chapter 3, hopefully. Okay. And if you have any questions, as usual, anytime you can contact me by WhatsApp. And I will be available tomorrow if you want. So for the person that asked for office hour, I will be there. Okay. Yes.
Where, Professor? Don't mind me asking.
Look,
In your office.
I will be in the engineering building in room 209. Bechtel 209.
What time approximately? What time
Okay.
approximately?
Around 3.
Deal, Professor. Thank you so
Okay.
much.
But just, I will always be around. Just send me a message and I can come.
Deal, Professor.
Okay.
Thank you.
Welcome.
Bye.
Bye bye.